Have you ever stopped to think about how every single digital device on the planet, I'm talking your phone, the internet, even satellites, all agree on what time it is? It's a much bigger deal than you think. Because if they're off by even a millionth of a second, the whole system can start to break down. We're going to dive into a brilliantly simple fix that keeps our entire digital world ticking with unbelievable precision. You know, in Alice in Wonderland, the White Rabbit was always late for a very important date. Well, in our world, that's not just a cute story. For things like the stock market, global communications, or even a rover driving around on Mars, being off by a microsecond isn't just an oopsie, it's a potential catastrophe. See, precise timing is the invisible engine that makes our modern lives work. And today, we're going to pop the hood and see how it runs. All right, so here's our game plan. First, we'll get into why timing is so dang critical. Then we'll hit the main roadblock, what I'm calling the microsecond problem. After that, we get to the really cool part, the totally counterintuitive solution. We'll see it in action, and then wrap up by looking at what this all means for building a more precise world. Okay, let's kick things off with this quest for perfect time. And look, we're not talking about being on time to the minute or the second. We are on a hunt for nanosecond accuracy. That's billionths of a second. So to keep all this stuff in sync, we lean on a few workhorse systems. You definitely use the Network Time Protocol, NTP, probably without even realizing it. It's the magic that keeps the entire internet humming along on the same clock, down to a few millionths of a second. For heavy-duty jobs, like industrial robots, there's something called PTP, which pushes for nanosecond precision. And for communicating in space, there's a special protocol that lets a Mars rover and an orbiter chat without any mix-ups. But here's the thing, they all run into the very same fundamental wall. And that wall is what brings us to the core challenge, the microsecond problem. It all boils down to the natural limits you hit when you try to measure time using software. Okay, get ready for a fun little paradox. Imagine you want to write the exact time you mail a letter, on the letter itself. Well, the most accurate time would be the very instant it leaves your fingertips and drops into the mailbox, right? But by then, it's too late. The letter's already gone, you can't write on it anymore. Digital data packets have this exact same problem. The hardware knows the precise nanosecond it left, but that info is only available a split second after the packet has already been launched into the network. So the standard way to handle this is with a kind of digital handshake. Think of it like a game of catch. Computer A throws a ball, which is a data packet, and writes down the time, T1. Computer B catches it at time T2, then throws it back at time T3. When computer A finally gets it back at time T4, it has 4 different timestamps. With a little math, they can figure out the travel time and get their clocks in sync.
But, and this is the big but, here's the flaw in the system. Those first timestamps, the I'm throwing the ball now times, they're recorded by the software a tiny fraction of a second before the physical hardware actually sends the packet out. It's like starting your stopwatch a moment before the runner actually leaves the block. That tiny delay, that little bit of software lag, is the source of the error that keeps us from reaching that perfect nanosecond accuracy.
So, how do you fix a problem that seems baked into the laws of physics? Well, the answer is just brilliant and totally counterintuitive. So let's really think about this. How can you possibly send a piece of information that you don't actually have yet? You need to put that super precise hardware timestamp in the message, but you only get it after the message is already gone. It really sounds impossible, doesn't it? And the solution is so simple, it's almost funny. You don't. You don't try to send the timestamp in the packet it belongs to. You just wait. And you slip the timestamp from the first packet into the second packet. This amazing little trick is called interleaving. Basically, the system just holds on to that super accurate hardware timestamp. We can call it a hard stamp, from the packet it just sent. Then, when it's getting the next packet ready to go, it just tucks that previous hard stamp inside. It's a one-packet delay that completely changes the game. So what does this actually look like? Theory is great, but let's see a little before and after to really get it. Okay, check this out. On the left, you've got the standard method, a nice, simple back-and-forth conversation. But now look at the right. That's the interleaved mode. See how the communication lines sort of crisscross? That's the whole idea in one picture. The timestamps from an earlier message are being carried by a later one. The data is literally being woven or interleaved together. This is where the magic happens. Every time a packet goes out, it's not carrying its own send time. Instead, It's carrying the super accurate hardware timestamp from the packet that was sent before it. By just delaying that information by one step, the system perfectly solves that too late problem. It gets to use the most precise measurement possible. And this little shift in thinking, this simple, elegant solution, doesn't just fix one thing. It unlocks a whole bunch of advantages and creates a much more precise digital world for all of us. So what are the perks? Well, they're huge. For starters, accuracy just skyrockets, jumping from the microsecond range right into nanosecond territory. It's also way simpler. You don't need all these extra follow-up messages just to confirm timing. And get this, it's backwards compatible, so it can automatically figure out if it's talking to an older system and just work. Plus, it's tough. It's designed to handle things like lost or duplicate data without getting confused. It's more accurate, it's simpler, and it's more robust. What's not to love?
You know, the engineer who came up with this, David L. Mills, he summed it up perfectly himself. He said the changes provide improved performance and reduced complexity. And the key was that interleaved design, sending the timestamp in the next packet. It's just a masterclass in elegant engineering. And believe me, this isn't just a concept in a lab. This exact principle is used in one of the most high-stakes, extreme environments you can imagine, deep space. It's part of what helps keep the Mars rovers perfectly in sync with the orbiters flying above them, communicating flawlessly across hundreds of millions of miles. So from your computer all the way to another planet, this simple idea is keeping time.
It really just goes to show you, doesn't it? Sometimes the biggest, most important breakthroughs don't come from throwing more processing power at a problem. They come from just looking at it sideways, a little bit backwards, and finding a simple, brilliant idea that was hiding in plain sight the whole time. It makes you wonder, what other huge challenges out there are just waiting for a simple shift in perspective?